Hi, welcome back. This is the last lecture on CUDA Essentials, and we're going to look at kernel execution, thread indexing, and CUDA vector types. The key points of this lecture are three. First, in a kernel, to determine which part of the array to work on or to determine different execution paths, we will need to obtain the thread ID. For that, we have to retrieve the ID of the block, the ID of the thread in the block, and do a simple math that is called thread indexing. Second, we need to keep in mind that the kernel execution, except for the CUDA data movement function, are asynchronous, so we might use synchronization to ensure correct execution. Third, CUDA provides vector types, similar to C structure with 2, 3, and 4 members, to improve the memory bandwidth. As we saw in previous lectures, CUDA uses the single instruction multiple threads paradigm. In this approach, each thread executes the same kernel function. However, we want to have a way for a kernel to operate on different elements of an input array or execute a different series of operations. The way to do that is to associate an ID to each thread and use the ID of the threads to access different elements of the input array. For instance, if we have an input array with 20 elements, we might want to have 20 threads to operate on 20 array elements in parallel. Thread 0 can take element 0, thread 1 can take element 1, thread 2 can take element 2, and so on and so forth. For this reason, we need to find a way to determine the thread ID number. The problem of determining the thread ID is called thread indexing. How do we find the thread ID? CUDA within the kernel allows to retrieve two index variables, blockIDX.x and threadIDX.x. to determine the ID of the block and the ID of the thread within the block. Knowing this, we can calculate the thread ID. But do we miss anything? Yes, within the kernel we don't have information about how many threads a block has. We can get this information from a so-called dimension variable, blockdim.x, that gives us the number of threads per block. Let's look at the practical example of finding the ID of a thread in blue in this diagram. In the main code, we launch a kernel using an execution configuration of 7 blocks with 256 threads. We see this in the triple angle brackets. When we write our kernel K, each thread needs to determine its own thread ID. The way to do that is to calculate first the offset to the first thread ID in the block by multiplying the block ID by the number of threads per block. Once we calculate the offset, we can simply add the thread ID number within the block, and voila, we have the thread ID number. Was easy, right? An important aspect of kernel launching is that kernel launching has an asynchronous execution. Asynchronous execution means that after the kernel execution, control returns to the CPU immediately after starting the GPU process, even before the kernel has finished executing. To synchronize all the threads or just part of the threads, CUDA provides two functions. First, CUDA device synchronize to synchronize all the threads in the GPU, and second, __ sync threads to synchronize all the threads within a block. The traditional example where we need a CUDA device synchronize is when we need to use printf in a kernel. We launch a kernel that does a calculation and then print the results. I don't want to disappoint you, but if you haven't tried yet, you won't have any print to display. The reason is the asynchronous nature of a kernel launching. A kernel launch is asynchronous. That means that the control returns to the CPU immediately after the launch, before the kernel has finished executing. So what is the next thing in the CPU after the kernel finish? Application exit. At application exit, GPU ability to send output to the standard output is terminated by the operating system. For this reason, the output that is generated later by the kernel has nowhere to go, and we won't see it. On the other hand, if we use CUDA device synchronize, then the kernel is guaranteed to finish, and the output from the kernel will find the waiting standard output queue before the application is allowed to exit. By default, CUDA data transfers, like CUDA malloc and CUDA memcopy, are synchronous. In other words, the functions do not return until the data transfer is complete. So, for instance, CUDA memcopy finish execution before the CPU can move to other operation. A nice feature of CUDA is the support of vector types to extend the standard C data types of length up to 4. For instance, if we want a vector with 4 elements of type float, we can use type float4. If we want to use a vector with two elements of type integer, we can use CUDA vector type int2. We can access individual components using the suffixes .x, .y, .z, and .w, like accessing members of a structure. Accessing components beyond those declared for the vector type results in an error. CUDA vector types really look like standard C structure, so it is legitimate to ask ourselves what the benefit could be in using them. It turns out that the use of vector types allows for vectorized loads and stores in CUDA, C, and C++, and helps increase the bandwidth utilization. So for this reason, we should use CUDA vector data types when it is possible. At this point, it might not be a surprise for you that for the index variables, block IDX and thread IDX, we use CUDA vector type. Index variables are 3 element vectors of type unsigned integer that correspond to the CUDA data type uint3. In addition, when I introduced CUDA grids, I mentioned briefly the type dim3. CUDA used the vector type dim3 for the dimension variables griddim and blockdim. dim3 type is a CUDA type that is equivalent to uint3 with an unspecified entry set to 1. dim3 variables are used for specifying execution configuration. This lecture concludes the CUDA Essentials series. In this lecture, we focus on 3 points. First, in a kernel, we will need to obtain the thread ID number. For that, we have to retrieve the ID of the block and the ID of the thread in the block and do the thread indexing. Second, we need to keep in mind that the kernel execution, except for the CUDA data movement functions, are asynchronous. So we might use synchronization to ensure a correct execution, like for instance printing from a device. Third, CUDA provides vector types similar to C structures with 2, 3, and 4 members to improve the memory bandwidth. In the next lecture, we will start working on our first program in CUDA. So talk to you in a bit.